students, now let's continue with the properties of prime and composite integers. Now in previous video we have seen the definition of prime and composite integer. So now let me take the first theorem in that. The statement of the theorem says, if P is a prime and if P divides AB, then either P divides A or P divides B. So, the proof of the theorem is, now here P divides AB, we have to prove either P divides A or P divides B. So, what given that this thing is given to us, P divides what? AB. Fine. Now if P divides AB, therefore by definition of divisibility, there exists K from set of integers such that what? AB is equal to what? P into that integer. Call it as equation number 1. Fine. Now suppose on a contrary, let us assume, suppose P doesn't divide A. So if we assume P doesn't divide A, our aim to show P divides B. So this gives our claim. What is our claim? We must show P divides what? B. If P doesn't divide A, because either or is here. Either P divides A or P divides B is here. So P doesn't divide A means we have to show P divides B. Fine. So now as P doesn't divide A, so we have written a note. So from that note, and P is what? P is prime. So from the note we have written P is a prime and P doesn't divide A, then the GCD of P and A should be what? 1. And I have given an example there of 3 and 4 also. Now this gives the GCD of P and A should be what? 1. If GCD of P and A 1, so this gives Px plus Ay is equal to what? 1. For some xy belongs to what? Set of integer. So now this gives Pbx plus Aby is equal to what? B. I have multiplied by B because I want to show that B is equal to some multiple of P or P divides B. That's why I have multiplied by B here. Now B is an integer, so we can multiply by that. Now I will substitute here AB as what? P into K from 1. So this gives P into B x plus, here we get P into K into Y is equal to what? B. Now from these two terms we can take P common. So P will be common. What we get? Bx plus Ky. Bx plus Ky is equal to what? B. So this gives P divides B. P divides B. Similarly, if P doesn't divide B. Now here we have assumed P doesn't divide A, we are able to show P divides B. Similarly, if P doesn't divide B, then we can show P divides A. This is the proof of this theorem. Now the next theorem we will take. The next theorem, the statement of the next theorem is that the statement of the next theorem is that if P is a prime and if P divides the product A1, A2, so on up to AN, if P divides the product, general thing we want, right? Then now we have proved that one for 2 integers. So here I want to take n integers. Then at least one integer among A1, A2, so on up to what? AN divisible by P. Divisible by P. So, proof of this is given that P is a prime. P is prime. And P divides A1, A2, so on up to AN. Now, here we will go for the previous, just like a previous theorem, then it needs many steps. So it's better to use here, let us use here a principle of mathematical induction on n, as these are n numbers, and n is what is n here? A suffix, which is a natural number. So we use this, prove this result using principle of mathematical induction. Principle of mathematical induction. Induction on n, as for n equal to 1, result is trivial. Result is trivial. Clearly, if n is 1, then only one integer is here. P is a prime and P divides A1. Fine. So the result is trivial. P divides A1 is same as to say at least one integer among these one divisible by P. Fine. Now for n equal to 2. For n equal to 2, then if P divides A1, A2, then we have to show either P divides A1 or P divides A2. So this is true from the previous theorem. So I can say, so by above result or above theorem, so by above or the previous theorem, so by previous theorem, result is what? Either P divides A1 or P divides A2. Fine. Therefore, this result is true for n equal to 2 also. Now assume that result is true for n equal to k. That is, if P divides A1, A2 and so on up to AK, then P divides AI for some I from what? 1, 2, so on up to k. For some I from 1 to k. Now this is our assumption. We will assume for n equal to k and we will prove it is true for n is equal to k plus 1. Now consider what we have to consider for k plus 1. Now consider P divides A1, A2 and so on up to AK plus 1. So now this part we will assume one integer. So from this it gives us P divides A1, A2 so on up to AK, or P divides AK plus 1. P divides AK plus 1. Now this is here P divides AI or P divides AK plus 1. For some I from 1 to what? K. This is from, I can say it as 1. From 1. Fine. This is our assumption here. We had used it. Now AI and AK plus 1 are here. So I can combine this result combining this, I can write P divides AI for some I from what? 1, 2, so on up to what? K and K plus 1 also. So, P divides some AI from these. Fine. Therefore, we can say result is true for n equal to what? K plus 1. Thus by principle of mathematical induction, result is true for any positive integer n. For any positive integer n, or what can we say? N belongs to set of natural number. For all n belongs to set of natural number. This is the proof of this one. Now in previous theorem we have proved the same one for 2 integers. Now here we have proved it for n integers using principle of mathematical induction. Now the next part is very important theorem. That one already we had used many times in school also, but here we will prove that one in terms of notation. That is fundamental theorem of arithmetic of unique factorization theorem. Fundamental theorem of arithmetic of unique factorization theorem. That one we have to start. So statement of this one, the statement of this theorem says every integer n greater than 1 can be written as product of prime factors and that representation into prime factors, that representation into prime factors is unique apart from the order of primes. Now what does it mean? We have already used this many times. Now suppose I will take the number 24. Now you know the 24, the prime factorization of 24 is 2 into 12. Again 2 into 2 into what? 6. The same one can be written as 2 into 2 into 2 into what? 3. So this is our prime factorization of what? 24. The same one can be done by other students as some students, suppose some student guess firstly itself that it is divisible by 2. But if someone is not able to guess that thing, so suppose that other student will start with 3. So it can be written as 3 into what? 8. So 3 into 8. So 8 he can be written as 8 is equal to 2 into 4. That is 3 into 2 into 2 into 2. After all, these are what? Same. So these are unique. Apart from the order. Apart from the what? Order. While this 3 takes last or 3 takes first or 3 takes in between, it doesn't affect. This is the part here. So every integer n greater than 1 can be written as a product of its prime factors. Every one can be written as the product of prime factor, but that representation is also what? Unique, but the order doesn't matters. order of the prime doesn't matters, which prime will come where, it doesn't matter, after all it is unique. Still the product of this one or the product of this one are same. That's why this is unique representation of prime numbers. These are what? The prime numbers. Now in school life we had used these one to determine GCD, to determine LCM and so on. Now let us see the proof of this. So the proof of this theorem, let n greater than 1 be any integer, n greater than 1 be any integer. First of all, we shall show that n can be written as a product of primes. Later on we will go for its uniqueness. So first of all let us show n can be written as a product of primes. So now for that, if n is prime, n is itself a prime number. Suppose n is prime, it is greater than 1 means it may be prime also. Then no need to show anything, nothing to prove. If it is a prime, then nothing to prove. Fine. Now, but another possibility is that n is what? Composite. Suppose n is composite. Then n has finite number of positive proper divisors. Finite number of positive proper divisors. Among these proper divisors, n has finite number of proper divisors. Among these proper divisors, choose least element. Say P1. Suppose the least one is P1. Therefore, as this is the divisor of n, so this P1 divides n. Therefore, n is equal to what? P1 K1. Where this K1 is not 1. And K1 lies between 1 and n, and it is what? An integer. Fine. Now here, then P1 must be what? P1 must be prime. Why? Because K1 lies between 1 and n. Then P1 must be prime. Fine. Now, let us show this P1 is prime. So to show this, suppose P1 is not prime. That is, P1 is composite. Then there exists a positive integer. Say d. There exists a positive integer, say d, such that d divides P1 and 1 less than d less than P1. D lies between. P1 is not prime, then it must be composite, because there are only two possibilities for positive integer, that it is either prime or a composite. So there exists a positive integer, say D, such that D divides what? P1, and that is not 1. So as D divides P1 and P1 divides N, and P1 divides N. So what does this say? D divides N. But D is less than P1. D divides N as 1 less than D less than what? P1. So D is in between 1 and P1. Fine. So but which contradicts to the fact that we have chosen the least element or the least proper divisor of N. We will name it as P1, which is a this thing contradicts to that thing. Therefore P1 must be what? Prime. Here our assumption is wrong. So P1 should be prime. So I can say which is a contradiction. Which is a contradiction to P1 is least positive. P1 is least positive integer dividing N. Therefore P1 must be what? Prime. P1 must be prime. Now here if K1, what? P1 is prime, N is written as P1 into K1. We had proved P1 is prime. Now what about K1? If K1 is prime, then N equal to what? P1 into K1 is product of two primes, product of two primes P1 and K1. But if K1 is composite, suppose K1 is what? Composite. This is also the possibility. K1 is composite. As we see here 24. So 2 into what? 12. So here this 12 is a composite number. 2 is a prime number. 24 can be written as a product of two numbers. So where one is prime, other one is composite. While if I take 6 can be written as 2 multiplied by what? 3. Where both are prime. So here we will stop, as this is the prime factorization of 6. So K1 is composite, then there exists a prime. Say P2, such that P2 divides what? K1. And if P2 divides K1, so this gives K1 is equal to what? P2 K2, where 1 less than K2 less than what? K1. 1 less than K2 less than K1. Now if again the question comes for what? K2. If K2 is prime, what we get? Then N is equal to what? P1 into K1 is replaced by this P2 K2 is a product of 3 primes. P1, P2 and K2. Again the question same. If K2 is composite, then there exists a prime. Say what? P3, such that P3 divides what? K2. that prime P3 divides K2. So as that divides K2, so K2 is equal to what? P3 K3, where 1 less than K3 less than what? K2. Fine. Now again, if K3 is prime, then n is equal to what? P1, P2, P3, K3 is product of what? 4 primes. Is product of 4 primes. P1, P2, P3 and K3. If K3 is composite, then continue above process. The same thing will repeats. So if it is composite, the same thing will repeat, since n is finite integer, this process should stop somewhere. Then suppose after ith step we get n is equal to P1, P2, P3 and so on up to what? Pi, where each Pi are prime. Prime. Fine. Now this is what the proof of our first part, that is n can be written as product of primes. Now we have to prove that this factorization is unique. So let us assume there are 2 different factorizations for this. So for uniqueness, this is again a proof, the same proof will continue here. Now to prove uniqueness, suppose n equal to P1, P2 so on up to Pr, and n equal to Q1, Q2 and so on up to what? Qk, and so on up to Qk. Fine. Where Pi and Qj are what? Primes. Pi and Qj are primes. I goes from 1 to R and J goes from 1 to Q. I from 1 to R and J from 1 to K respectively. Fine. Now as here n equal to this one and here also n equal to this one, so their left hand sides are same, so their right hand side should be same. Therefore we get P1, P2 so on up to Pr is equal to Q1, Q2 so on up to what? Qk. Call it as equation star. Suppose now that is, I can say it as P1 into P2 so on up to what? Pr is equal to Q1, Q2 so on up to what? Qk. That is P1 into X equal to Q1, Q2 so on up to what? Qk. P1 into X. Now here this x is what? An integer. All prime numbers are after all what? Integers. Here x is equal to what? P2, so on up to what? PR, and this is what? An integer. As this is an integer, so this implies P1 divides what? Q1, Q2, so on up to what? Q2. And if P1 divides this one, P1 is a prime number. So by previous theorem, what can we say? P1 must divide at least one of the integer among Q1, Q2, so on up to Qk. So since P1 is prime and P1 divides Q1, Q2, so on up to what? Qk. Therefore, then P1 must divides at least one integer, among Q1, Q2 and so on up to what? Qk. Fine. Now suppose P1 divides Q1 and both are prime. So we know that if P1 divides Q1 and both are prime, so P1 must equal to what? Q1. And as P1, Q1 both primes, therefore this gives P1 equal to what? Q1. We have seen that note after the definition of prime numbers. If both are primes and they are divisors, one of them is divisor of other, then they must be what? Equal. So P1 equal to what? Q1. And if P1 equal to Q1, then here what we get? Here these may cancel. So we get, therefore P1 equal to Q1, therefore what we get? Star implies, I can say star implies P2, P3 and so on up to what? PR is equal to Q2, Q3 and so on up to what? Qk. These many remains there. Again, this also can be written as P2 divides Q2, Q3 and so on up to what? Qk. Here also we can take this as another integer. We can write it as since what can I write here? Since P2 is prime and P2 divides Q2, Q3 and so on up to what? Qk. Then P2 must divides at least one integer among Q2, Q3 and so on up to what? Qk. At least one among Q2, Q3 and so on up to Qk. Now again suppose P2 divides Q2. But P2, Q2 are primes. So this gives P2 equal to what? Q2. Therefore again this star gives what? P3, P4 so on up to what? PR is equal to Q3, Q4 so on up to what? Qk. Continuing above process, continuing this process, if R less than K, then in rth step then in or after rth step we get 1 equal to what? QR plus 1, QR plus 2 and so on up to QK, which is impossible. Why does this impossible? Because product of this primes is what? 1. It is not possible. These all are what? Primes, and the product of primes won't be 1, because we know 1 is not a prime number. So here, because QR plus 1, QR plus 2 and so on up to what? QK are primes. Thus what can I say? R must equal to what? K, and we have Pi is equal to what? Qj for all I and j. Pi must equal to what? Qj for all I and j. So here our theorem will prove. So finally I must write thus what can I say? Every integer n greater than 1 can be written as a product of prime factors. And that representation is what? Is unique, and that representation is unique up to the order of primes. Now this result is also true for the non-positive integers, means what? The negative integers. So that thing let me write as an remark. So this statement is also true for the negative one. So let us write a remark for that, or the note. Remark: the fundamental theorem of arithmetic, unique factorization theorem is also true for what? Non-positive integers. Okay, that is, if n is non-zero integers with n not equal to plus minus 1, then n equal to plus minus p1, p2, so on up to what? Pr, where Pi is what? Prime. Pi is prime. I goes from 1 to R. This is the proof of the fundamental theorem of arithmetic unique factorization theorem, and that is true for the negative integer also. Okay, now in next video we will see some more definitions and some results again that are also related with the prime numbers. Okay, now here we will stop for today. Thank you.